Okay, students, in this session we are going to focus on the very important concept related to the relative motion. In the relative motion, you will be having many different applications like Rainman concept, aircraft wind problems, next kind of closest approach, and a river boat problems. So let us see one by one in detail. Now, as a part of important applications related to relative motion, first I am going to take the very important information related to river boat numericals, right? Usually while solving problems related to river boat, majority of the students will commit mistakes due to not having a proper idea as well as proper knowledge in framing the figure as well as in applying the concept. Okay? So now in this session, I am going to take everything in detail, the entire concept related to river boat based applications, so that you can solve any kind of problems easily. Okay? So in the next few minutes, you are going to become expert in doing almost any kind of applications related to river boat. Not only river boat, even if you go to the numericals related to aircraft and wind based problems, even those concepts also will get covered. Why? Because on comparing river boat and aircraft wind numericals, only the changes you need to do is replace boat with aircraft and replace water with wind. That's it. Now, coming to river boat applications, first I am going to take the case 1, where let us consider a river having width d is flowing like this towards right direction. This is the flow of river I am taking, right? And let also consider the velocity of the water in the river flow is equal to VW you take, right? Next, let us consider this is the x-axis, means the direction flow of river is x-axis, and along the width of this, let us consider this is y-axis. Now you take, this is the point A and this is the point B. Now a boat started at point A and it wants to reach point B. Point B in the sense, you take this is one bank of the river and this is other bank of the river. The target of the boat is to go from point A to point B. Like almost water is flowing along this horizontal direction and along AB, perpendicular to water flow. The boat wants to go from here to here. So if you analyze the motion of the boat started at point A, if the boats keep moving like this, let's consider the boat is moving like this, or let us take the boat started moving along AB initially. So when the boat started moving along AB, right, due to the water flow, there is a chance of displacement in the position of the boat. If boat started traveling along AB due to the water flow, right, the boat may get displaced, due to which it keep traveling like this in this direction. Suppose if water flow dominates, then there will be no chance of reaching the boat to the other side. So that's why in order to reach the other bank, all the time the boatman has to keep the boat against to the flow of water like this. So this is the suggestible direction of the boat, right, relative to water, suggestible direction of the boat relative to water, so that he can reach the other bank easily. Because when the boatman all the time keeps direction of the boat again is to the flow of water, slightly at an inclination theta with AB, due to the flow of the water, because water flow is in this direction, no? If you take velocity of the boat with respect to water like this, then due to water velocity, the boat can reach the other bank. Means net velocity will be somewhere in this direction. So in the process of doing any problems related to the crossing the boat, right, when the boat is crossing a river, then the minimum and basic idea is all the time the boatman has to keep the direction of the boat against to the flow of water, so that flow of water will help the boat to reach the other end. Due to which here we can expect three types of velocities. While solving the problem related to river boat, you will expect three types of velocities. One is VW. Let us consider VW is the velocity of boat with respect, velocity of water. We have taken VW, no? So let's you take velocity of water here with respect to ground. Velocity of water with respect to ground. This is absolute velocity. VW is the velocity of water with respect to ground, and VB is equal to, let us consider, velocity of boat with respect to water, with respect to ground, this one. So these are absolute velocities. Usually when we do the problem related to river and boat, the basic velocities we can assume are net velocity of the boat with respect to ground, velocity of water with respect to ground. Apart from these two, you will be also having one more velocity, that is VBW. This is the velocity of boat with respect to water. So in fact, this is the relative. So all the time, the velocity that will be maintained by the boatman. Let us consider the boatman started his boat at point A, and if he is moving against to the flow of water at an inclination theta relative to AB, then whatever the velocity you observe with the boat is VBW, not VB. Listen carefully. If you were given a statement like velocity of water, velocity of boat in still water, very frequently you will be given this statement, velocity of the boat in still water. So many people think that still water means water is at rest, so that they will treat this as VB, so that the problem will go wrong. Actually, if you were given like velocity of boat in still water, so this will be VBW. All the time remember this. This is a very important note. If you were given any velocity of the boat in still water, that will be VBW, but not VB. VB is a net velocity, right? And if the boatman is taking the boat like this, then this will be also VBW. If you were given that the boatman started with so and so velocity in the water and moving, then that will also be VBW. So identifying VBW and VB is very, very important. Of course, there will be no ambiguity in understanding VW. Velocity of water will not have any relative. It's a standard, absolute. But coming to boat velocity, two velocities will be there. One is net velocity, means with respect to ground. VB is with respect to ground. And velocity of boat with respect to water. Two velocities will be there. So basing on that, we will take these three velocities. Now in this figure, if the boatman is always keeping the boat in this direction, then it is taken as VBW. Okay, and this is a VW. Let us see some important mathematical part related to this. During the crossing of a boat, right, across AB or along AB or along width of the river. Here in this case, consider D is the width of the river. So see, in the Next figure I am going to take this as the standard assumptions, like d will be the width of the river, VBW velocity of boat with respect to water, this is absolute velocity of the boat, and this is absolute velocity of water. So clear up to here? This is analysis. Now let us see the mathematical part for solving the various cases in this, right? So case 1, let us consider a general case I am taking, this is. After that case 2, case 3, I am going to show you the specific cases, right? So this is the general case we have analyzed up to now. So let us see the next case. Continuation. Let us see the general case continuation only. The necessary mathematical part and all I am going to show you. This is case 1. Like before case itself, I am continuing the necessary mathematical part. This is the general case where the boat started at an inclination theta relative to AB, right, with value VBW, and take this is x-axis, and along AB take this as y-axis, because we are going to see some vector related information here. That's why I am assuming this as x-axis, nothing but it can be represented with I cap direction, it will be represented with j cap direction. So AB is the width of the river, and this is the VW, velocity of water in the river. Now you see, from the knowledge of relative motion, we can write VBW is equal to velocity of boat with respect to water in vector form, can always written as velocity of the boat minus velocity of the water. These two are absolute velocities. So this is a formula from the knowledge of relative motion. You can write velocity of boat with respect to water as VB minus VW in vector form. This is in vector form I am taking. Because once if you draw figure relative to the vector form, automatically the analysis will become easy. And any kind of problem can also be solved easily. So now in this, since we have assumed this is a direction of VBW, this is VW at an inclination theta with respect to AB. So therefore, here we don't know what is VB. VB is a velocity with respect to the ground. In order to calculate VB here, you can write like this. VB in vector form is equal to velocity of boat with respect to water plus velocity of water. This you can take. Here let us consider net velocity of boat is equal to velocity of boat with respect to water plus velocity of water, like this. So our target is to find out this VB, net velocity or absolute velocity. Before that, try to write down VBW in vector form and VW in vector form. So by taking this as the coordinate system, you can write VW is equal to here. Velocity of water can be written as in vector form, simply magnitude of velocity into I cap I can take. This is the velocity of water. And similarly, velocity of boat with respect to water can be written as, listen carefully. So this is the velocity of boat with respect to water. Now, if you resolve it, then along this direction and along this direction, this would be VBW cos theta you can write, and this would be VBW sin theta you can write. That's it. VBW cos theta and VBW sin theta. This is along y-axis, this is along x-axis. Then here, if you write specifically VBW in vector form, let us write VBW only in the vector form. Here we resolved it along AB and along this direction. Then you can write magnitude of VBW, next sin theta into minus I cap I am taking, because this side we have considered plus I cap. So this side it would be minus I cap, right? Only the vector form I am representing here. And plus, even you can write VBW cos theta into j cap. This is plus j cap because upward AB is along positive y-axis, right? So this will be the vector form of velocity of boat with respect to water in general case, where the boatman is keeping the boat against to the flow of water. So that velocity of flow of water will help the boat in reaching the opposite bank. That is the motto of the boatman. Now here you can write velocity of water is equal to magnitude of velocity of water into I cap. You can take like this. This is magnitude of velocity of water into I cap, because this is the flow of water. No? Now VB is equal to, right, this. If you want to find the absolute velocity of boat or net velocity of boat with respect to ground. See, I'm just making use of entire vector analysis. Okay. This is a general case where boat is moving in this direction. Means the boatman, the driver of the boat, is all the time keeping the boat in this direction. Okay. Next, here water is flowing horizontally, right, which is fixed value. Now if you want to find out the net velocity of the boat with respect to the ground, we will use this formula from the knowledge of relative motion. Then VB can be written as VBW plus this one. No? So make use of this. This can be written as VBW sine theta into minus I cap plus VBW cos theta into J cap, right, plus VW. VW is pointing along x-axis, that's it. So therefore, final value of VB would be, take I cap common, then you will write like this, VW minus VBW sine theta into I cap plus VBW cos theta into J cap. That's it. This is the absolute velocity of the boat. Identifying this is very, very, very important. I've taken this as the absolute velocity of the boat. You just take it as first equation. Right? VW minus VBW sin theta into I cap plus VBW cos theta into J cap. This is absolute velocity of the boat. Now say from here we can conclude that you can expect the absolute velocity of the boat somewhere in this direction, you see. Most probably you will expect this direction. See, I'm writing it in the blue. Somewhere like this in XY coordinate system, this would be the direction of absolute velocity of the boat, VB direction, because it is having X component as well as Y component. It's okay, minus X component, like VW minus VBI. Right, it is in the first quadrant. Some magnitude into I cap plus J cap. It is in XY plane in the first quadrant. Means even though the boatman all the time keeping like this the direction of the boat, due to the flow of water, the net velocity of the boat is going in this way. Right. Let's consider it is reaching somewhere here. Let it be point C. The boat is reaching opposite back somewhere here. Because you see, from this vector information we can conclude that velocity of the boat is not along AB. It is having non-zero I component and non-zero J component. So obviously the direction would be expected in the first quadrant, due to which the destination will be somewhere here C, not at B. But actually the motto, of course, the motto of boatman is to take to other side. Along AB or slightly inclined at AB, that is not an issue. But in the general case, if all the time boatman is keeping like this at an inclination, then flow of water is fixed, due to which this is a net velocity. Therefore, the boat will reach somewhere at point C. It's okay. This is with respect to the ground. Let us consider BC is equal to some X. Here X can be taken as the drift. Technically this is very important. You will be asked in many problems directly the drift. Drift is the lateral displacement taken by the boat in the process of going from point A to point B due to flow of water. Right, this BC, the drift is mainly due to flow of water. This is VW minus VBW sin theta. That component is taking the boat along BC. Actually the target is A to B. But due to flow of water, all these things are happening. So that's why I told this is a general case. This is a general information. Right? So now in this case, from here we are going to two more specific cases. And in fact, examination point of view, those two specific cases are very important. Okay? Remember this one. From here I am going to do everything related to riverboat. It is a general case where if the boat starts at an inclination theta, Due to flow of water, it will reach somewhere at point C. In that x is called as drift. Calculation of the drift is also one of the very important applications related to riverboat problems. Okay. Now from the figure, if you want to calculate the drift, this one, the x is equal to, along x-axis, no, you can take like this. If t is a time, let us consider t is a time taken to cross the river in the given situation. Then, if you take t is the time taken to cross the river, I'll write a little bit down. Then time is equal to, time taken to cross the river, t is equal to, you can write, I'm taking width of the river d. If I take width of the river d, then d by velocity along d you will take here. You will take time t is equal to width of the river d by velocity along this direction, along AB, nothing but you are having this value, j component, this value, or you can take this value. In the process of crossing the river, the boat is covering a displacement of AB, shortest distance. And what is the value of velocity along AB? VB cos theta, because j cap. This component is not helping to cross. This component is helping to displace from B to C. This component is taking the boat from B to C, and this VBW cos theta is taking the boat from A to B. Therefore, you will write here time is equal to d by VBW cos theta. That's it. This is a way of calculating the time. If you were asked what is the time taken by the boat to cross the river, you will use this formula directly. Time taken by the boat to cross the river is d by VBW cos theta. From this only you can conclude. And again the lateral displacement x is equal to, here, what is x? This BC. This would be the x, and x can be written as this one, VW minus VBW sin theta into this time. This is second observation. These two are very important. So in the general case, we have taken formula for time to cross the river, as well as in the process of crossing the river, whatever the lateral displacement has taken place BC, this lateral displacement is calculated. Fine. If you remember, if you have idea on this information, the rest of the cases can be solved easily. Two more cases are there which are going to be solved from this knowledge only. This is a 1 point, second and third. Better you take this as second. So already we have taken this as first, no? Right. See, this I have taken first, take this as second, take this as third. Remember those three observations? And clear about these three observations? Simple logic. In relative motion, boat will have two speeds, one relative to water, another relative to ground, and it reaches the other bank along the direction of relative to ground, not relative to water. This is relative to water. The boatman can take the boat or can ride the boat along VBW. If the boatman is taking in a specific direction, don't take it as VB, take it as VBW, relative to water. And take water direction, then by using this formula, calculate VB. After that, time is nothing but, this is in crossing AB, this width, right? Here VBW cos theta, along J component, velocity along J component is helping. That's why time is equal to distance by speed. And here x is lateral displacement. This can be written as, this I component is helping the boat to displace from B to C. That's why I've written that. Okay. Now this is case 1 general case. Let us take case 2. Case 2, case 3, I'm going to take specific cases that will help you in problem solving. Usually case 2, case 3 will be asked. Right? Okay. Next. Let us take case 2. In the case 2, I'm just focusing on shortest time. I just wanted to take shortest time in which the boat is crossing the river. And case 3, I'm going to take shortest path. Because now the boat has the choice whether to cross the river in shortest time or along shortest path. In the case 2 I'm assuming that boat is crossing the river in shortest time. That is T minimum I am taking. This one. So now let us see the condition. In the previous slide, we have seen the time taken to cross the river is dB by VBW cos theta, where theta is angle between VBW and AB. This all information you need to keep in mind. Your time is d by VBW cos theta. Right. So shortest time means first try to take the time. Time we have seen in the previous slide as VBW cos theta. Now in the case 2, we must calculate T minimum. And in this formula, VBW usually will keep it fixed, constant, no acceleration, right? D width of the river is constant. Then we can write here, T is inversely proportional to cos theta. Is it or not? That means on increasing theta, time decreases. On decreasing theta, time increases. Because in the previous case, we have just seen that the boat started moving along inclination theta. But about specifically theta, right? We have not mentioned any value. About theta, we have not taken any specific value. Is it or not? We took a general case. Now in this specific and general case, theta is not at all mentioned. By taking a general value, you got time like that and x like that, second and third. But in the present situation, case 2, we need to focus on only shortest time. Shortest time taken by the boat to cross the river, where you can write T is inversely proportional to theta. Now you got the importance of theta. Here when cos theta is maximum, that is +1. If you take cos theta as maximum, then time would become minimum. Therefore, directly you can write that minimum time taken by the boat to cross the river would be d by VBW. Right. You can take like width of the river by VBW. That's it. This is a minimum time taken by the boat to cross the river. I hope you are already having this idea. T minimum is equal to d by VBW. That's it. What is the minimum time taken by the boat to cross the river is d by VBW. Condition is, in order to have cos theta +1, theta must be 0 degrees. So now if you want to draw the figure for this situation, then according to our observation, theta must be 0, no? Here theta 0 is nothing but the direction of VBW will be along AB. This will be the figure. And this is VW, due to which the boat reaches, right? Here the boat will reach the other bank kind of this direction. Let us consider this would be the direction of the boat. Means this would be the net velocity of the boat. It's okay. This is a point C. And this is X. X is a drift during minimum time. But in the previous slide, we have seen X is a drift in general case, where theta is not equal to 0. When theta is not equal to 0, this is X and T is this one. Now in the present case, since we have taken theta is equal to 0, VBW will be always point along AB. That means the conclusion is, if the boatman wants to take the boat to the other bank in shortest time, he must keep all the time boat along AB direction. The boat must be kept along which direction? AB, perpendicular to the flow of water, so that he will reach the other bank easily. Easily in the sense in shortest time, quickly. Because see, the figure itself is showing that in this case, VB will become, the magnitude of VB will become, it is taken along hypotenuse, this will be 90 degrees. Value of this will become VBW square plus VW square. That's it. Since hypotenuse is the longest side in a right angle triangle, no? Compared to VBW and VW, VB is the highest value. It has taken along the hypotenuse. Therefore, the magnitude of the velocity when boat is crossing in shortest time is given by that one. VBW square plus VW square. And T minimum is given by D by VBW. And in this, even you can write VBW is equal to under root of VB square minus VW square. You just make VBW as the subject, so that VBW will be like this. Therefore, T minimum can be written as from here D by VBW, or else D by under root of VB square minus VW square. This is a way of calculating T minimum. That's a very important case. So time taken by the boat to cross the river in minimum time or shortest time is given by that formula. And the condition is the boat will cross the river in minimum time when VB is all the time, or when the boatman keeping all the time along AB, perpendicular to the flow of water. This is very important note. Boatman has to keep all the time perpendicular so that reaches other bank in shortest time, right? And during the shortest time, drift would be, X is a drift during the shortest time. This is the drift in T minimum. How much lateral displacement has taken place means X is equal to, you will write it as distance is equal to speed into time. VW into T minimum you can write like this. X is equal to, in this way you can write, and X can be VW into T minimum, we have taken like this. That is D by VBW. So that X in minimum time can be written as D into VW by VBW. That's it. So this is going to be the X value, that is the drift in shortest time. In the previous case, drift in general case, when the boat inclined at an angle theta to AB. But when theta becomes 0 and the boat all the time moving along AB, in that case, the drift produced will be D by VW by VBW. Is it okay? Right. Next. So in this case too, these two are the important observations. Take it. Minimum time taken to cross the river is that one, and during minimum time the drift will be this one. In the case 2 you can take this as first observation, this as second observation, and this is the condition. Right, important. This is the condition for shortest time. Let us take case 3, shortest path. That's it. General case, case 1, case 2 enough. You can solve almost any problem related to river boat. Case 3 will be shortest path. Copied? Copy it fast so that I will shift to next slide. This important. How about your 2 more friends? I think you people having some festival, no? Today or yesterday night? That Jagar something. Yesterday night. You didn't slept? Yesterday night? Okay. I forgot, and just morning I came to know that. Let's see. Completed? Then take case 3. This is the right. So in the case 3, let us focus on calculating shortest distance. If the boat want to cross the river in the shortest distance or shortest path. Let's focus on this. In the case to shortest time, now shortest path. So just to visualize, if the boat wants to cross the river in shortest path, no doubt AB is the shortest path, is it or not? So all the time the net velocity of the boat must be along AB. The condition is VB, not VBW. VB must be along AB. When VB is along AB, then only it can reach the other exactly opposite end. For that, definitely the direction of VBW must be like this. You can take like this is VBW I am taking, and this is VW. And let us consider this is angle theta, some theta I am taking. Identifying this theta is very important now. It's okay. Here the task is shortest path. Shortest path means, let us analyze from here. I'll go to the previous slide. See. Here in the general case we got x is equal to VW minus VBW sin theta into t. Is it or not? And this is x lateral displacement due to the flow of water. So in order to reach in shortest path along AB, x must be 0, no? If it is reaching shortest path, there shouldn't be any x value. It shouldn't get laterally displaced. It shouldn't have any drift. Then only we can conclude that the boat can reach the other bank in shortest path. It can go from A to B in shortest path when the value of x becomes 0. So x is equal to VW minus VW sin theta is there, no? So let us solve here itself. You just check what happens when x is equated to 0. You equate it to 0 so that you will write this as VW minus VBW sin theta is equal to 0. Like this you can write. Because t always it will become 0. VW minus VBW sin theta into t must be 0. From here try to take sin theta as the subject. If you take sin theta as the subject, then you will be getting VW by VBW. So the selection of theta should be in such a way that if it satisfies this condition, like sin theta is equal to VW by VBW, then the boat obviously reaches the other point in shortest path. Clear? From general case you can simplify. Otherwise also not an issue if you take the present case shortest path. Here also you are going to get the same thing. If you calculate sin theta in this triangle, you will be getting VW by VBW. This is the sin theta value. Velocity of water by VBW. Or else, during shortest path, the selection of theta must be like this. Sin inverse VW by VBW. That's it. If the boatman all the time keeps the boat along this direction, then the boat will reach the opposite bank in shortest path. And if you want to calculate time, sometimes you will be asked to find out or to calculate time when the boat is reaching the opposite end in shortest path. This is equal to d by, time is all the time d by VB you will write. Along AB the net velocity is VB. While calculating the time you must take VB over here. Okay? Right. Next. And again from this triangle you can even write VBW is along the hypotenuse. VBW square is equal to VB square plus VW square. Here if you make VB as the subject, then under root of VBW square minus VW square. So this would be the VB. Then time taken by the boat during shortest path can also be written as d by replace VB with this value, so that you will be getting under root of VBW square minus VW square. That's it. Now see, if you understand the general case correctly, the specific cases second and third are simple. Okay. In the direct riverboat based problems, second case, either second case or third case will be given. Usually you will be expected easy to moderate level sums in this riverboat concept. Not difficult. Only chances in difficult. First slide, done. Wait. That's it. This is the first slide. I'll share you the PDF, no problem. Anyway, you took the picture? Right. This is the next slide. And this is the next slide. Shortest path. And this is shortest time. Only 3 slides. Got completed the topic. Let us focus on Rainman concept. Shall I continue Rainman concept? Coming to riverboat, this one and Rainman concept are really very important. Okay. Otherwise, we'll discuss Rainman concept over there. In another class, there we'll discuss. Okay. Enough.